Okay, today we're going to talk about inertia. This goes along with one of Newton's three laws of motion. And so as we get started here, what I would say is that inertia is a word that many people use that they may not completely understand. It's one of those things that's used in common usage, but a lot of people that use it don't really understand what it's referring to. So I want you to think a little bit about what you think of when someone uses the term inertia. Like I said, like a lot of things, this is just a property of matter. So what Newton did when he sat down to figure out his three laws of motion is he basically said, what happens to an object if essentially nothing happens to it? By that I mean, there's no forces acting on it, there's nothing pushing it or doing anything to it at all. Well, what you have to understand is that with inertia, it's just going to keep doing what it's doing. And so understanding this concept is really important if you're looking to come up with a full understanding of what motion is and how it changes. And again, you guys can always pause the video if you need to, if you're taking notes. So I want to take just a minute and talk about Isaac Newton just a little bit. Isaac Newton's really an interesting guy, and I would say that in the last 400 to 500 years, he was one of just a few scientists who truly, his brain worked differently. He saw things. He was insightful in a way that other scientists of his day weren't. And so he built his first law, his first law of motion, around this concept of inertia. Now, when did he come up with this? Well, Newton was around in the last half of the 1600s. And what happened during this period of time is that there was a pretty major plague, a disease that went through London. He was an Englishman, and his family did have some money. And so when this plague started to ravage London, he decided it's time to get the heck out of town, and he went to the country house of his family, and he stayed there for 18 months. And to give you some idea about what you're capable of when you really focus on something, during this 18 months, Isaac Newton developed the three laws of motion that we're talking about in this chapter. He also essentially invented calculus. So he came up with the rudiments of calculus, the structure of calculus. He figured out how gravity worked, and actually devised a formula that allowed him to calculate gravitational pull, all in 18 months. So he was very accomplished. I guess you could say this is what you can do when you don't have the distraction of the internet always after you. So Newton was a brilliant guy. He didn't always get along, though, like a lot of geniuses. He didn't get along all that well with the people around him. And so he was a member of something called the Royal Society, which I don't know how this would sound to you, but it would sound terrifying to me, which the Royal Society still exists today, was actually a group of scientists. And as they wrote papers or decided, wrote thesis on how different things worked, they would get up in front of the rest of these other scientists and present their papers. It's kind of like these days, if you get a master's degree and you have to defend your dissertation. You put yourself out there, and the other people sit there and critique your work. I mean, they criticize where it's appropriate. They give you credit where it's appropriate, that kind of thing. And that sounds terrifying to be judged by your peers like that, but it actually is what makes science better. By testing those ideas and by taking that critique and changing the way that people did their research, science got stronger. And so Newton didn't really take much to that because he was smart and he knew he was smart. And so he didn't really like the critique much. And sometimes the critique really wasn't appropriate. Like there was professional bias and a little bit of jealousy going on. So he didn't get along real well with his fellow scientists of the day. But as he sat down to write down his three laws of motion, the very first one, like I said, he focused on what would happen to an object if it wasn't moving. What made it move is what he was focusing on also. And so before Newton and a few other people, what most people thought is that you had to have some force acting on an object to keep it moving. I wish I could remember where I saw this. It must have been in an old textbook or something. But I once saw a painting from the early 1600s. And it was two people. And one person was throwing a ball towards the other person. And you could see the other person was in the act of trying to catch it. The ball was in midair. Well, at that point in time, what they believed is that there had to be a force acting on that object to keep it moving. That any object required some force to keep it going. Because they didn't understand what that force might be at the time, they actually, in the painting, had little fairies, little angels almost, or cherubs with wings, and they were behind the ball pushing it from one person to the other person. They didn't really understand the way that motion worked. And so, like we've done for millennia, they come up with an excuse for it or some possible reason, and when they couldn't explain it, they used fairies. So Newton, though, came along, and he basically said that, this isn't the way that it works. And he actually borrowed a lot of this first idea from somebody else. In your guys' crossword, I think it may have mentioned him. The guy he borrowed much of this first law from was Galileo. So Galileo Galilei, basically, he conducted what's called a thought experiment. And what he did is he imagined, if I have a block, I'm talking just like a block of wood, and I push it across a table, that it'll slide for some distance until it finally stops. Now, if I take that block, and again, this is Galileo thinking this through, if I take that block and I make it smoother, like today we think you sand it down, you sand that surface a little bit so it's smoother. You sand the table that you're sliding it across so it's smoother also. He said, then if I pushed it with the same force I did before, it'll slide across the table, but because it's smoother, it'll slide even further. So if I sand it some more, both surfaces, and I slide it again, because it's even smoother, it goes further still. And he imagined, and this is why this had to be a thought experiment, he imagined, what if I had a block and a table that were infinitely smooth, that basically it had zero friction. Again, this is why it had to be a thought experiment, because it's not possible to do that. But he said, if I push that block across that infinitely smooth table, it would continue to go, it would continue to slide across that table and move forever if the table was big enough. So he comes up with this idea that says, I don't need a force to continue to push it. Once it's moving, it'll just keep moving. All right? So Galileo comes up with this concept that an object really doesn't need a constant force pushing it along to keep it moving. Once moving, it'll just keep moving. Okay? So you could kind of see the same thing. If Galileo would have lived somewhere maybe in the Alps and not in the lowland area of Italy, he might have been able to slide something across ice. If you've ever watched someone hit a hockey puck and watch that puck slide across the skating rink or a hockey rink, it'll just slide all the way from one end to the other, really without slowing down much at all, because that ice has such low amounts of friction. So Newton's going to kind of borrow this idea. Maybe that's a better word than steal. But Newton borrows this idea from Galileo. Now, the guy that they basically were against here, against is a bad way to put it, that they were disproving, let's say, was someone else you've probably heard of, and that's Aristotle. Aristotle had basically argued for almost 2,000 years at this point. His original thoughts about this had held. And he basically said that you have to have a force to allow a moving object to continue moving. Now, what Aristotle was basically thinking is, if I notice that every time I push something, if I stop pushing, it stops moving. And what he didn't really recognize was the force of friction that would always counter that movement and require a force to keep you going, to overcome that friction. But what both Galileo and Newton said is, you know what, if you don't have friction, you don't need that force. So is it possible for an object with no force acting on it to be moving? The answer here is, yes, it is. If you don't have any force acting on it, it will just keep moving at the same speed, at the same velocity would be a better term, that it started at. So what will a force that I apply to an object, what effect will that have on the object? Well, if we apply a net force, we saw when we talked about the basics of forces, that if you apply a force, you get an acceleration. Okay? So if I kind of look at this, is a little bit of a busy slide, but I'm just using this kind of to show two forces. If I think about an airliner, for instance, the engines on an airliner are going to propel that airliner forward. It exerts a force on that airliner called thrust. The air going past the airliner is going to produce a force in the opposite direction called drag. Now, what would be true if the forward thrust equaled the backward drag? What if those two forces were equal to each other? Well, if they were equal, those two forces would essentially cancel out each other. So if I have zero force in the left to right direction from our diagram here, all I would say is this airliner would continue to move. It's not like it would drop out of the sky. It would continue to move in the forward direction at constant velocity. Okay, constant velocity. If your forces total zero, meaning both of these together, if they total zero, you will get no acceleration. All you're going to get is a constant velocity. So this would be, if you're on an airliner flying from the East Coast to the West Coast, then what I would basically say here is that if you were in this situation where those two forces were equal, you're going to cruise along at whatever airspeed you're at. So let's say 400 miles an hour. So it seems like, and some people won't understand this, but you could say, if you maintain a certain speed, whether that's 400, 500, 200, if you maintain a certain speed, these two forces must be equal to each other. Because imagine what would happen if thrust was bigger than drag. Well, I would get a net force in the forward direction, and I would accelerate. My speed would change. Okay? If drag was bigger than thrust, so you crank the engines down, and I get more drag, more friction. We'll talk more about this later. But I get more drag than I do thrust, this airplane's going to slow down. Again, its velocity is going to change. It experiences an acceleration. Okay? Same thing go for the vertical forces that are acting on this airplane. So basically you have weight that's going to pull you down. The weight of this aircraft is going to, that's a force of gravity acting on this airplane is called weight. And I must have an opposite force to that going upward if this is going to stay in the air. All right, we have a name for that. It's called lift. So as long as those two vertical forces are equal but opposite, we're going to maintain the same altitude. If I want to come into land, I need to decrease lift and allow weight to pull us downward. Okay? Again, the point here is that I could have an airplane that has no force acting on it, and yet it's still flying through the air. with constant velocity. All right, so here is Newton's first law, written much as he did, and you've probably heard this before. It says that an object at rest remains at rest. An object in motion will continue in motion with constant velocity. This is the part no one ever includes. They say an object at rest remains at rest. An object in motion remains in motion. But they never give the end part. That motion is constant. You're going to have a constant velocity. And this is unless the object's going to experience some kind of net external force. All right, it has to experience this force if you're going to have a change in velocity. Okay, Newton's first law. And Newton rested and realized that he was very, very intelligent. So I would say this now. Does a stationary object have inertia? An object that's not moving. You're probably sitting in your chair right now and you're not moving anywhere. Do you have inertia? Think about that for a second. And I will tell you that a basic definition of inertia is how much you resist changing your motion. So do you have inertia? The answer here is a most definite yes. Okay, you may have seen this before. It's kind of like a magic trick. You have a whole table that's been made up, and they're going to basically try to remain in that state. They are objects at rest, okay? And they're going to have a particular amount of inertia. Now, we can determine how much inertia, we can give a value to inertia if we look at a particular property of matter. What property of matter can we use to help us gauge how much inertia that something has? All right, how much inertia something has. Now, think of it this way. If I need to make somebody move, if they have high inertia, it's going to be difficult to get them to move. So think about people. If I want to make something that's not moving start to move, what kind of object is going to be difficult to do that with? All right? It's always going to be an object that has a lot of mass. It's mass that determines how much stuff that you're made out of, that determines your inertia. All right? So mass determines your inertia. If you look at this fella, if you want to do this trick, be careful what you're pulling on. But I will tell you that typically if you rip that tablecloth out from under all the stuff on the table, it's going to be the stuff that has a lot more mass. That I'm going to use the word heavy, even though that means weight. But the stuff that has more mass is going to be more likely to stay in place. So for instance, if you do this with a plastic cup that has no water in it, that's going to be pretty light, and it's more likely to move due to the small amount of friction that you have between the tablecloth and the bottom of that empty plastic glass. If you want to do this trick, you're better off filling up that glass with about half a glass of water. That makes it have more mass and means it's more likely to stay in place. Okay? So mass is determiner of how much inertia that you have. So this has real impacts in terms of different things that we see around us. So for instance, if I have a small car, I would say because the mass of that small car is much, much lower than the mass of a great big truck, that this small car is going to resist changes to its velocity much, much less. It's going to be easier to make it change its velocity than a great big truck. All right, so you also see this in race cars. In a race car, it's all about changing your velocity. You want to be able to accelerate as quickly as you can, which means you don't want a lot of mass. You want that mass to be as low as you can have it. So this small car is going to be able to accelerate more easily than the big truck. And this has real impacts on the components of these vehicles. So for instance, if I want to drive this car and go from, let's say I'm merging onto the highway or something, so I'm going to go from 0 up to 65 miles an hour, and I want to be able to do that in an acceptable amount of time. Basically what I'm talking about is a VI and a VF and a delta T. If I want to have that acceleration, that is the formula for acceleration, then I need to put a certain size engine in it. And because it doesn't have a lot of mass, I don't have to put a huge engine inside of this little car. On the other hand, this big truck could weigh 80,000 pounds. It could weigh 40 times what that little car weighs. And that means in order to get an acceptable acceleration for the big truck, I have to put a much bigger engine in it. I have to get more force out of that engine to get the kind of acceleration that I want because of that higher mass that it has. Okay? Secondly, if you look at the brakes, if I want to stop these vehicles, the brakes on a little car like this, you could fit in the palm of your hand. On the other hand, the brakes that are on a big truck, on these wheels on the big truck, they're going to be half the size of the wheel itself, and you're going to have two of them, one on either half of the wheel. So it takes much more force to get you to stop and accelerate and experience that negative acceleration. An acceptable negative acceleration is going to be, you're going to have much larger components on the vehicle. Okay? So one last example that I'm going to go through here. I want to review that forces thing. Let's say that we've got an aircraft that's flying due north, constant velocity, constant altitude. Does this does this aircraft have any forces that are acting on it? I think it would defy reason to say that it doesn't. We already kind of talked about this a bit on the previous slide, but I know I have weight pulling this down. I have lift pushing this back up. I have thrust pushing the airplane forward, and I have drag pulling it back. So I basically know that I have 4 forces acting on this airplane. And yet it's flying at constant velocity. So this is kind of a check on your understanding. How is that possible, folks? That I have 4 different forces acting on this aircraft, and yet it continues to have a constant velocity. I want you to think in your head, how's this possible? Because this is an important part of understanding Newton's first. All right, I've got those 4 forces acting, and yet there is no acceleration. Again, pulling on that previous example, the only way this is possible is if the forward thrust is equalized by the backward drag. If the downward force of weight is equal to the upward force of lift. If all of those forces cancel each other out, which is what I just described, what's going to happen in terms of acceleration? Well, if they all cancel each other out, I don't have a net force. My net force is 0. And so, because my net force is 0, as Newton would say, that object in motion remains in motion because you have no outside force acting on it. They all cancel each other out. Okay? So again, if you see an object moving with constant velocity, you know immediately that all the forces acting on it have to be 0. I could use you as another example. You're sitting there in your chair right now watching this video, and yet I know there are forces acting on you. I know that gravity is pulling you down. All right, that's again your force of weight. Weight is pulling you down towards the center of Earth. And yet, when I watch you guys in Zoom meetings, you're not plummeting into the ground. I don't see you disappearing from your camera's frame there. You're sitting there not moving. So that tells me immediately, not only do you have your own weight pulling you down, there must be another force that's acting to oppose weight. All right, we're going to learn that's called the normal force. But I know it must be equal but opposite to gravity, since I can observe that you are not accelerating in one direction or the other. All right, so again, This kind of sums this up. If you have any change in velocity, that means that you must have a net external force acting on the object. And that would basically, when I say net external force, I mean you're going to add all of the external forces that are acting to you or acting on you, and they can't total zero if you're accelerating. Okay? So if you get a change in velocity, you know that there is a net force and that the sum of all the different forces acting on you cannot total zero if you are accelerating. Again, you guys can take a moment and pause it if you want to write down anything. What I can also say is we have a condition that's called equilibrium. And so while if your net external force doesn't equal zero, you're going to get an acceleration. But when you're at equilibrium, that basically means that your net external force is equal to zero. So in this case, of course, you will not get an acceleration. This is essentially what I just talked about using you guys as an example. You, if you're just sitting there not moving, you're an example of an object that is in the equilibrium state. Okay? All the forces acting on you cancel, which is why you're not accelerating. You're at equilibrium. Okay, now this example, folks, I am going to do in a separate video. So we're pretty much done with Newton's first law. Remember that Newton's first law basically says that an object in motion will remain in motion, an object at rest will remain at rest. And that is as long as you have no net external force acting on you. That would cause an acceleration. So you're going to stay at rest if you have no force acting on you. That's how you'll remain. All right, so until the next video, I will see you guys later. Have a great rest of your day.